This isn't just a thought experiment, it's a blueprint for humanity's survival. A vision so audacious that it makes our boldest dreams seem small. Freeman Dyson didn't just imagine capturing starlight. He imagined swallowing it whole. A sphere around our sun, a shell of pure engineering ambition that could power civilizations for millions of years. But this wasn't science fiction dreaming. This was cold, calculated physics from one of the most brilliant minds of the 20th century. And today, as we stand at the edge of an energy crisis that could define our species' future, Dyson's concept isn't just fascinating, it's essential. The problem is staring us in the face. Our planet burns through energy like never before. Every year we consume more. Every year we need more. And every year the gap between what we have and what we need grows wider. Solar panels cover rooftops. Wind turbines spin across landscapes. Nuclear reactors hum in the distance. But it's not enough. It will never be enough. Not for the civilization we're building. Not for the future we're racing toward, unless we think bigger, unless we look up. Freeman Dyson understood something most people miss. Energy isn't scarce in the universe. It's everywhere. Streaming from every star, radiating through space, waiting to be captured. The problem isn't that there's no energy. The problem is that we're thinking too small. We're trying to catch raindrops when we should be damming the river. We're harvesting crumbs when we should be claiming the entire feast. And the feast is our sun. A nuclear furnace that burns 600 million tons of hydrogen every second. A power plant that has been running for 4.6 billion years and will keep running for another 5 billion. The ultimate energy source, the final answer to humanity's power needs. But there's a catch. Our sun doesn't just shine on Earth. It shines in every direction, into the void, into empty space, into nothingness. Of all the energy our sun produces, Earth captures less than 1/1000th of it. The rest is lost. Wasted. Gone forever. It's like standing next to a waterfall and trying to fill a cup with a teaspoon. Meanwhile, the waterfall roars past, untouched, unused, unstoppable. Dyson looked at this cosmic waste and saw opportunity. He saw the greatest engineering challenge in human history, and he saw a solution that would change everything. The Dyson Sphere, not just a satellite, not just a space station, a megastructure that would dwarf anything humanity has ever built. A shell around our sun designed to capture every photon, every ray, every particle of energy our star produces. It would be the largest construction project in history. Larger than cities, larger than countries, larger than continents. A project so vast it would require resources from entire planets. Technology we're only beginning to understand. Cooperation on a scale our species has never achieved. But if we could build it, if we could actually construct a Dyson Sphere, we would solve the energy problem forever. Freeman Dyson wasn't a dreamer. He was a physicist, a mathematician, a man who worked on the atomic bomb and helped design nuclear reactors. When he proposed the Dyson Sphere in 1960, he wasn't writing science fiction. He was writing science, cold, hard, calculated science. He looked at the numbers and realized something profound. Any advanced civilization would eventually face the same problem we're facing now. They would outgrow their planet's energy supply. They would need more power than their homeworld could provide, and when that happened, they would have only one choice. They would have to capture their star. This wasn't just theory, it was prediction. Dyson believed that any civilization advanced enough to build a Dyson Sphere would eventually build one. Not because they wanted to, because they had to. Because the alternative was energy poverty, stagnation, decline, the slow death of technological progress. He called it the inevitable next step in cosmic evolution, the graduation from a planetary species to a stellar species, the moment when a civilization stops living off the scraps of starlight and starts consuming the whole star. But Dyson's vision went deeper than engineering. He saw the Dyson Sphere as a search tool, a way to find other civilizations in the universe. Because any species advanced enough to build a Dyson Sphere would leave a signature, a fingerprint in the cosmos. Their star would dim. Its light would change. Instead of radiating visible light in all directions, it would glow in infrared. The heat signature of a captured star, the unmistakable mark of a Type II civilization, one that had mastered stellar engineering, one that had solved the energy problem once and for all. The physics behind it is surprisingly simple. Stars are just nuclear reactors, massive fusion engines that convert hydrogen into helium and release energy in the process. Our sun produces about 3.8 times 10 to the 26th power watts. That's 380 followed by 24 zeros, a number so large it's almost meaningless. But here's what it means in practical terms. If we could capture just 1 second of our sun's total energy output, we could power human civilization for millions of years. 1 second. That's the difference between energy scarcity and energy abundance, between the civilization we are and the civilization we could become. The challenge isn't the physics, the challenge is the engineering. How do you build something around a star? How do you construct a sphere 186 million miles in diameter? How do you move materials across interplanetary distances? How do you coordinate construction in the vacuum of space? How do you prevent the whole thing from falling into the sun? These aren't theoretical problems, they're practical ones. Engineering challenges that would test every limit of human technology, human organization, human endurance. Dyson himself understood this. He knew the sphere wouldn't be built in a day, or a year, or even a century. It would be a generational project, a challenge that would span multiple lifetimes, multiple civilizations. It would require advances in materials science, robotics, space travel, and artificial intelligence. It would demand new forms of international cooperation, new models of resource allocation, new ways of thinking about what humanity could accomplish when it worked together toward a common goal. The materials alone would be staggering. Current estimates suggest a Dyson Sphere would require the equivalent of disassembling an entire planet. Not Earth, something smaller, maybe Mercury, maybe the asteroid belt. But still, the raw materials would have to come from somewhere, and they would have to be processed, shaped, transported, and assembled in space, without gravity to help, without an atmosphere to breathe, without the safety net of a planetary surface below. Some critics called it impossible, too big, too expensive, too dangerous. They pointed to the technical challenges, the resource requirements, the sheer audacity of the concept. But Dyson had an answer. He never said it would be easy. He never said it would be cheap. He never said it would be safe. He just said it would be necessary. Because the alternative wasn't just energy scarcity, it was evolutionary stagnation, the slow decline of a species that had reached the limits of its homeworld and decided to stop growing. The energy crisis we face today proves Dyson's point. We've reached the limits of Earth-based energy. We've harvested the easy sources. We've built the obvious solutions. Solar panels, wind turbines, nuclear plants, hydroelectric dams. But we're still hungry, still growing, still demanding more power than our planet can provide. And as our civilization advances, as our technology becomes more sophisticated, as our population grows and our ambitions expand, that hunger will only get worse. Other civilizations must face the same choice, the same moment of decision. Do they accept the limits of their homeworld? Do they slow their growth, reduce their ambitions, accept energy poverty as the price of staying home? Or do they reach for the stars? Do they take the leap from planetary to stellar civilization? Do they build the megastructures necessary to power their next phase of evolution? Dyson believed the answer was obvious. Any civilization advanced enough to face this choice would choose growth. They would choose expansion. They would choose the stars, and they would leave evidence. The dimmed light of captured stars, the infrared glow of civilizations that had graduated from planetary to stellar status, the unmistakable signature of species that had refused to accept limits. This is why the Dyson Sphere matters, not just as an engineering challenge, not just as a solution to the energy crisis, but as a test, a measure of what our species is capable of, a question that will define our future. Are we the kind of civilization that accepts limits? Or are we the kind that builds spheres around stars? The concept has evolved since Dyson first proposed it. Modern versions include swarms of solar collectors instead of solid shells, rings instead of spheres, partial constructs instead of complete enclosures. But the principle remains the same. Capture the star, harness its energy, use that power to fuel the next phase of human evolution. The transition from a single-planet species to a multi-system civilization. The jump from Type 1 to Type 2 on the Kardashev scale. The moment when humanity stops being limited by the energy resources of one world and starts being powered by the energy resources of the cosmos. We're not there yet. We're not even close. But we're moving in that direction. Every solar panel we install, every wind turbine we build, every nuclear reactor we design, every step toward clean energy is a step toward the Dyson Sphere. Not because we're building it now, but because we're building the technology, the expertise, the global cooperation necessary to build it someday. We're learning to think bigger, to engineer on larger scales, to coordinate projects that span continents and decades. The question isn't whether we'll build a Dyson Sphere. The question is when, and whether we'll do it before we run out of alternatives, before the energy crisis becomes an energy catastrophe, before we're forced to choose between growth and survival, because that choice is coming. Maybe not in our lifetime, maybe not in our children's lifetime, but it's coming. And when it arrives, we'll need to be ready. We'll need to have the technology, the resources, the will to reach for the stars, to build the impossible, to capture the sun itself. Now let's explore the engineering reality behind constructing a Dyson Sphere. This isn't just about dreaming big anymore. We're talking about the most ambitious construction project in human history, one that would fundamentally reshape our understanding of what's possible. The scale alone defies comprehension. A Dyson Sphere around our sun would require materials equivalent to dismantling entire planets. We're not talking about mining asteroids or harvesting metal from the moon. We're talking about completely deconstructing rocky worlds like Mercury, Venus, maybe even Earth itself. The raw materials needed would dwarf every construction project humanity has ever attempted combined by factors of millions. But here's where it gets really fascinating. The engineering challenges aren't just about scale. They're about precision at an astronomical level. Every component of this megastructure would need to maintain perfect orbital mechanics while withstanding radiation that would vaporize any material we currently use. The structural integrity requirements alone would demand materials that don't exist yet, substances stronger than diamond, lighter than carbon fiber, and more heat-resistant than tungsten. Think about the logistics for a moment. Traditional construction relies on fixed foundations, stable ground, predictable conditions. A Dyson Sphere has none of that. Every beam, every panel, every connection point would be floating in the vacuum of space, subject to solar winds, gravitational perturbations, and the constant bombardment of cosmic radiation. The construction crews wouldn't be working from scaffolding. They'd be operating in three-dimensional space around a star that could kill them instantly. The manufacturing infrastructure required would be unlike anything we've ever built. We'd need orbital factories, space-based mining operations, and transport systems capable of moving materials across distances that make intercontinental shipping look like carrying groceries across the street. The entire asteroid belt would become our supply depot. Mars might become a staging ground. The outer planets could serve as material processing centers. Robot armies would handle the actual construction. Millions, maybe billions of autonomous construction units, each one more sophisticated than anything we've built today. They'd need to work in perfect coordination, assembling components while orbiting a star at thousands of miles per hour. One mistake, one miscalculation, and entire sections could spiral into the sun or drift away into interstellar space. The power systems for construction alone would be staggering. We'd need energy sources capable of running this massive industrial operation, while the very structure we're building is designed to capture that energy. It's like building a hydroelectric dam while the river is still flowing. Except the river is a nuclear furnace and the dam is larger than any planet. Quality control becomes a nightmare when your construction site spans millions of miles. How do you inspect welds when the nearest section is further away than the moon? How do you ensure structural integrity when you can't even see the entire project from any single vantage point? The testing protocols would require sensor networks more complex than anything we've ever deployed. Weather doesn't exist in space, but solar storms do. Coronal mass ejections would be like hurricanes hitting a construction site. Except these storms carry enough energy to shut down entire power grids on Earth. Construction would need to halt, equipment would need to be protected, and workers would need to shelter or evacuate. The construction timeline would be dictated not by human schedules, but by the temperamental moods of a star. The assembly sequence becomes critical. You can't just start building randomly and hope it works out. The entire structure would need to be assembled in a specific order, with each section providing structural support for the next. It's like building a house of cards, except each card weighs millions of tons and is positioned thousands of miles away from the others. Material transport presents its own set of impossible challenges. Moving construction materials from Earth to the construction site would be like trying to supply a city by carrying supplies one backpack at a time. The energy cost alone would be prohibitive. We'd need space elevators, orbital launching systems, and propulsion technologies that make our current rockets look like fireworks. The thermal management systems would be crucial. Parts of the sphere closest to the sun would experience temperatures that melt steel, while sections in shadow would freeze colder than liquid nitrogen. The entire structure would need thermal regulation systems more sophisticated than anything we've ever designed. Heat would need to be distributed, absorbed, and radiated away in carefully controlled patterns. Communication across the construction site would require networks spanning millions of miles. Signals would take minutes to travel from one side of the project to the other. Coordinating work crews would be like trying to conduct an orchestra where the musicians can't hear each other. The entire operation would need to be choreographed in advance, with backup plans for every possible contingency. The construction workforce would be unlike anything in human history. We'd need engineers who understand orbital mechanics, materials scientists who can work with substances that don't exist yet, and project managers capable of coordinating the largest undertaking in human history. The training programs alone would take decades. The expertise required would span every field of human knowledge. Safety protocols would be revolutionary. Traditional construction safety involves hard hats and safety ropes. Space construction safety involves radiation shielding, emergency evacuation to the nearest planet, and survival systems that can function in the vacuum of space. The insurance alone would bankrupt nations. The environmental impact would be unprecedented. We'd be reshaping the entire solar system, altering the gravitational balance, and changing the way sunlight reaches every planet. Earth's climate would be affected. Mars might become more habitable. The asteroid belt would disappear. We'd be playing God with celestial mechanics. But here's the most incredible part. Despite all these challenges, the physics actually works. The engineering is possible. The materials science is advancing. The robotics are developing. Every single obstacle we've discussed is a problem of scale and complexity, not fundamental impossibility. The timeline would span generations. Children would grow up, have families, and grow old while working on the same construction project their grandparents started. It would become humanity's defining characteristic, the thing that unites our species across centuries of effort. The economic implications would reshape civilization. Traditional concepts of scarcity would disappear. Energy would become essentially free. The construction project itself would become the primary economic driver, employing billions of people across multiple planets and creating entirely new industries we can't even imagine today. So the real question isn't just whether we can build a Dyson Sphere, it's whether we should, because once we cross that line, there's no going back. The implications stretch far beyond engineering. A civilization capable of harnessing the full output of a star doesn't just solve energy problems, it fundamentally alters what it means to be human. We're talking about a species that can literally move planets, terraform worlds at will, and expand across the galaxy without ever worrying about fuel or power. But here's what keeps scientists awake at night. If we can build this, then other civilizations probably already have. And if they have, where are they? This is the heart of the Fermi paradox. We should see these megastructures everywhere, glowing like beacons in the infrared spectrum. Yet when we scan the cosmos, we find mostly silence. Maybe we're the first. Maybe we're alone. Or maybe something else is at play. Some researchers suggest that advanced civilizations might choose different paths. Instead of building massive shells around stars, they might focus inward, creating virtual worlds that require far less energy but offer infinite possibilities. Why dismantle Jupiter when you can build paradise in a computer simulation? There's also the possibility that Dyson Spheres represent a trap. A civilization that commits to such a massive project might become locked into a single star system, unable to adapt when their star begins to die. They become prisoners of their own success, tied to a structure so vast and complex that abandoning it becomes impossible. The environmental implications are staggering. Even if we somehow source all the materials without destroying planets, we're still fundamentally altering the solar system. Earth would exist in perpetual twilight, receiving only the carefully controlled energy that the sphere's operators choose to transmit. Weather patterns would shift dramatically. Ecosystems would collapse and rebuild. The very concept of seasons might disappear. Then there's the question of control. Who owns the sun? Who decides how much energy each planet receives? A Dyson Sphere isn't just an engineering project, it's the ultimate expression of centralized power. The entity that controls the sphere controls everything. Every factory, every city, every home depends on their decisions. This level of power concentration could lead to unprecedented tyranny or unprecedented prosperity. The psychological impact might be even more profound. Humans evolved under an open sky with the sun as a distant but reliable presence. Living inside a constructed shell, knowing that every ray of light is artificial, that the cosmos beyond is hidden behind layers of machinery, could fundamentally alter human consciousness. We might become a species that's forgotten what it means to see stars. Yet for all these concerns, the physics remains compelling. The energy crisis is real. Climate change is accelerating. Population growth continues. At some point, even the most optimistic renewable energy scenarios hit fundamental limits. The sun produces more energy in 1 second than humanity has used in its entire history. That's not a resource we can ignore forever. Recent discoveries have added new urgency to these calculations. We've found thousands of exoplanets, many in habitable zones. We've detected organic molecules in interstellar space. The universe appears to be teeming with the potential for life. If we're going to explore it, if we're going to spread beyond Earth and ensure our species' survival, we need energy on a scale that only stellar engineering can provide. The first steps might be surprisingly modest. Instead of a complete sphere, we might begin with orbital rings or partial shells. These smaller structures could capture a fraction of the sun's output while we develop the technology and infrastructure for larger projects. Each success would build confidence and capability for the next phase. The timeline remains daunting. Even with exponential technological growth, we're looking at centuries or millennia. But that's not necessarily a problem. Humanity's greatest achievements have always been multi-generational endeavors. The cathedrals of medieval Europe took centuries to complete. The Great Wall of China was built over 2 millennia. A Dyson Sphere would be the ultimate cathedral, a monument to human ambition that spans the solar system. The search for extraterrestrial intelligence has already begun incorporating these ideas. Astronomers now routinely scan for the infrared signatures that would indicate artificial structures around distant stars. So far, we've found tantalizing hints, but no definitive proof. Every anomaly gets investigated, every unusual light curve gets scrutinized. Perhaps the most profound implication is what success would mean for human identity. We would become the first species in our local group of galaxies to achieve true stellar civilization. We would join the ranks of hypothetical Type 2 civilizations, entities so advanced that they can manipulate the fundamental forces of nature. We would be the architects of artificial worlds, the masters of stellar engineering. Freeman Dyson himself understood this. His sphere wasn't just about energy. It was about humanity's place in the cosmos. It was about taking responsibility for our own survival and growth. It was about refusing to accept the limitations that nature imposes and instead choosing to transcend them through intelligence and engineering. The question isn't whether we can build a Dyson Sphere. The question is whether we can build it wisely. Whether we can maintain our humanity while wielding the power of stars. Whether we can create a future worthy of the incredible sacrifice and effort such a project would require. Because once we capture the sun, we become something new, something unprecedented, something that the universe has never seen before. We become the civilization that turned a star into a tool, that transformed the solar system into a machine, that took the first definitive step toward becoming masters of the galaxy itself. The age of planetary civilization would end. The age of stellar civilization would begin, and everything we think we know about limits, about possibility, about what it means to be human would change forever.